We proved rigorously that the homogeneous homomorphisms from H1 to H1 have the following special matrix form. It's block diagonal and the last entry is exactly determinant of the submatrix 2 by 2 submatrix on this corner. There are important consequences of this. This matrix can never have rank equal to 2. Either it's the zero matrix, pretty trivial, or it is rank 1, which means then everything gets crushed into a subspace in the xy plane, or it is a full rank 3 matrix. Another consequence, very curious one, is that the determinant is never negative. That means homogeneous homomorphisms from H1 to H1 are always orientation preserving. We have the proof, obviously, of this, but sometimes you want to see why something happens. You have to connect it to the geometry of H1. What is it about H1 that prevents any such homogeneous homomorphism from reversing the orientation? And that I answer in this lecture. In my argument, I will make use of the already proven fact that L maps the xy plane into xy plane. The horizontal plane has image contained in the horizontal plane and never mixes with the t-axis. So that was easy to prove, in fact, from homogeneity, and that I will use in my argument. So let's imagine L is a linear map from R3 to R3 that happens to be a homogeneous homomorphism of H1 onto H1. Take a curve, a geodesic Lipschitz curve that joins the origin to some point on the t-axis. We famously know that its projection is a circle in the xy plane, drawn in red here. Now L is Lipschitz both as a map from R3 to R3 and as a map from Heisenberg group to Heisenberg group, the second claim being not as easy as the first. But we take this as truth. Now, the restriction of L to the xy plane will map this projection circle to some ellipse containing the origin. And we know that the image of gamma will be the lift of the image of this projection. So the horizontal lift of this ellipse will be a curve that has projection exactly equal to this ellipse, and because of the way orientation works, it ends up on the positive t-axis. So we see that I and j directions are mapped preserving the orientation because the circles are the same direction, and then also the k direction is also preserved. So this makes determinant of L positive. The orientation is preserved. Now, if the restriction to the xy plane reversed the orientation, the image of the projection circle would be an ellipse parameterized in the other direction. And LO gamma is still a horizontal lift of this projection, and it will end up on the negative side of the t-axis. Now here we see that when you look at the IJ, the map L has reversed the orientation on that plane, but then it also has reversed the orientation on the t-axis. K direction has mapped to negative k direction. So it's double reversing of the orientation, and therefore the product of these two will be positive, and ultimately L is again preserving the orientation. So the reason homogeneous homomorphisms, or to be specific, the real reason is being Lipschitz. The reason linear Lipschitz maps from H1 to H1 preserve orientation is that the third component is determined uniquely by projection onto xy plane. Any Lipschitz curve in Heisenberg group is uniquely determined by its projection. And that is the true reason why these maps have to be orientation preserving.